Good morning, everyone. Now it is time to start our third unit. It's about diffraction. It's a very familiar concept for you. With the definition, it is the deviation of light from its rectilinear path and it's spreading out around obstacles. And since light spreads out around its object, around the obstacles, the shadows are not sharp. Or in other words, you will see some intensity modulations around the shadows. That's what we want to study in diffraction. If you look at this picture, it's a schematic representation of what diffraction is. Here we have a light source, which is a laser source, which has a plane wavefront. That's falling on an aperture, which is essentially will act like a source for us. And from that source, the light, okay, so it's going to be a point source because the opening is supposed to be small. And in that case, the light spreads out from this opening or our virtual source as a spherical wavefront. And these spherical wavefronts or the electric fields of the light tends to interfere, just like what we have learned due to superposition. That's what we have learned in interference. And it's going to produce a pattern which has a maximum and many secondary minimas on both sides of the main beam or the central peak. This is what you will see on the screen, and we will call this the fringes or diffraction fringes. This is the situation, and we want to learn how we can adopt some of the physical principles to explain diffraction. And suppose if you have a larger aperture, okay, suppose the aperture is bigger than what we have seen here, then again you will have something like more or less a flat intensity distribution, and towards the edges of this of the shadow you will see fringes, and that's what we call diffraction. And this is an example here in this picture. What we have is an example of the Fresnel diffraction of circular aperture. You will see very nice circular patterns of fringes. Okay, here we express Fresnel diffraction. There is a distinctive features for Fresnel diffraction, and the other one which is called Fraunhofer diffraction. We will see that in the later classes. Essentially, it deals with a near field or far field pattern, near field or far field source for diffraction. And Fresnel has explained this diffraction by Huygens principle together with the principles of interference, essentially the principle of superposition of waves. That is the first thing that we want to learn, that is the integral theorem of Kirchoff, or what we call, we can attribute it to something called Huygens Fresnel principle, and it expresses, the principle expresses the solution of homogeneous wave equation at an arbitrary point P in terms of the values of the solution and its first derivatives at all points on boundary on arbitrary closed surface surrounding B. Okay. Don't be confused with that or puzzled by that statement. What it says is that, okay, well, suppose we have to find the field distribution at one particular point P after the source. This is our obstacle that makes the source which emits a spherical wavefront. And one of the Huygens principle says that each point in the wavefront will act like sources of secondary waves. What it means is, suppose we have this opening as the source, then each point in this source will act like sources of secondary waves, secondary spherical waves, because these are point sources, and what is emitted from there will have to have a spherical wavefront. And that is, I have drawn it for the first one, and if you draw it for the second one, you see you get this. And if you draw it for this third one, you get something like this. And there will be, and the Huygens principle says that there could be infinite number of, or a large number of sources like this one. And the electric fields corresponding to, for example, the first source here and the second source here try to interfere, and that will make a central maxima and secondary minima on around the edges. Ideally, what you should have had is, when the situation like this happens, the light comes in and you should have a sharp central maximum, like the intensity is maximum there, and intensity should have been 0 here. But due to the secondary sources or the spherical wavefronts emitted by the secondary sources, the light spreads out into the shadow region here, and you can clearly observe the superposition and the interference, or what we call the diffraction patterns on this region, in the shadow region. That is what is in this here. Suppose we have an arbitrary point P, we can express the solution of the homogeneous wave equation. Wave equation is something that determines the propagation of the wave. You know what it is? It is very simple. Okay, it's a very simple equation. Del square y equals 1 by c square dot square y over dot t square. And suppose if we're talking about a function y, the values of the solution and its first derivatives at points on the closed surface surrounding P. Now we consider a closed surface, let's say a spherical surface or any arbitrary surface surrounding the point P, and you can express the intensity distribution or the intensity at the point P in terms of a solution and its first derivatives at all points on the closed surface, on this surface. Or ideally, the surface will act like secondary sources, and that electric fields will interfere and superimpose and will produce a certain intensity at this point P. That's what it says. The basic idea of Huygens Fresnel theory is that light disturbances at point P arises from the superposition of secondary waves that proceed from a surface situated between the point and the light source. Okay, now the situation was like this. Okay, you have a slit or your source, and you make the slit part of, okay, this slit part of a surface surrounding the point P. This is your point P, and we'll have to find out. Okay, then there will be secondary sources from this here, okay, and also region here, region here, region here, and the intensity or at this point P will be contributed from the secondary waves from all the surfaces, and we'll proceed to derive such an equation. Okay. It is basically sum of all the secondary waves, or sum of the electric fields of the secondary waves from the surface to from the surface that is reaching the point P. We'll see later that the relative contribution will be very high, or the only contribution that will come from all around the surface is going to be the source itself from this region here. Okay. But now we have talked about wave equation, and you may have to derive something called a time dependent wave equation, which we are familiar with in many branches of physics. For that, you consider a monochromatic scalar wave uxy e to the power minus I omega t. Substitute that into this one, and del square u e to the power I omega t will be the second left hand side, and on the right hand side you will have, since there is a second derivative with respect to t, there will be 2 I minus I omegas and u e to the power minus omega. This one and this will cancel out, and therefore what you will get is the scalar wave equation, which is del square plus k square is equal to u, and that is the time independent wave equation. Now the next thing that we will use is Green's theorem. Green's theorem is something that relates the surface integral and volume integral of certain things. Okay, this is how you may have learned it. This is how you. This is what Green's theorem will tell you. The volume integral of this quantity here, u and u prime. U and u prime are monochromatic scalar wave functions. Scalar wave functions, continuous first and second derivative, partial derivative. Okay, this is second order as first order partial derivative. Then the Green's equation tells the volume integral of this quantity here will be equal to the surface integral of this quantity here. Here u and u prime are two scalar wave functions. Now here we have used dou by dou n, where n is a unit vector, the direction of the unit vector, inward unit vector, which is perpendicular to the surface at all points. Okay, here it is like this, and here it is like this, and each point you have to do the surface integral. No, sorry, the component, the normal component of the gradient. That is what is meant by these two equations. Okay. This is essentially, this is another way of representing it. Di u prime by di n means the normal component of the gradient of at the surface is this one times u minus u prime. And in that case, it's easier to remember. U Okay, here you have volume and del square. Okay, and u prime del square u. To remember Green's theorem, it is volume integral, and here it is surface. Then you have del n u minus u prime del n u prime along the surface ds. Now you have the Green's theorem. One more thing which I want to stress is that we are talking about a scalar wave function. But we know that the electric field of an electromagnetic wave or the magnetic field are vector quantities. They are not scalar quantities. But here we use only the scalar quantities because to make things simpler. The derivations including this vector quantity is tedious, and therefore we will talk about the scalar wave functions, and also with the advantage that u square will represent the intensity at the point. Ultimately, around the object, what we are interested is in the intensity redistribution and the general behavior of the wave function. That is usually can be done with a scalar wave function. That's why we use scalar wave functions instead of vector wave. Now we have this wave equation, time independent wave equation del square u, and we have two functions u and u prime, and you substitute that, which means del square u is minus k square u, del square u prime is minus k square u prime, and if you substitute this 2 into the left hand side of Green equation, this becomes u prime minus u prime k square, and this becomes minus of minus u prime k square, which means the left hand side of Green's theorem becomes 0. Therefore, what is left is the right hand side, and the Green's theorem therefore reduces to simpler form for our situation, where u and u prime both obeys or behaves according to the wave equation, or when they are wave functions. This is what you get. Now you can solve for u at the point P. Okay. Now you go back to the concept. You need to have a surface around the point P, and the contributions of the waves at the point P is from secondary sources situated around the surface. Okay, here we have chosen a very arbitrary source, arbitrary surface. That surface is enclosing the volume that we are interested in. And here we have V is the volume, P is the point on the surface, and a point inside the volume. U and U prime are scalar wave functions within the volume. And also, in order to apply Green's theorem, it needs to have continuous first and second order partial derivatives within the volume and on the surface. Now, okay, these secondary waves are spherical waves. Therefore, we consider a spherical wave function. And this S here, remember, it doesn't represent the surface. It is actually the distance from the point P to the surface S. Okay, that's the distance. It's a small letter s. The surface is usually represented by the capital letter S. Okay, that is x. S is the distance from P to the point xyz on the surface. Now there is a problem, because when s equal to 0 means it is the point P, and when s equal to 0, because this is in the denominator, the at the point P, if this is the point P, this wave function is going to shoot up in its value, is going to go to infinity, and therefore we can say it has a singularity at s equal to 0. Now theoreticians find a way to avoid this singularity, and therefore, since you have to avoid the point s equal to 0 somehow, otherwise it's going to be a problem. How do you avoid that? We make a second surface. Okay, surround the point P by a small sphere. Here you have an arbitrary surface, but for the sake of convenience, we use a spherical surface around P and extend the integration throughout the volume between surface S and S. Okay. Here you have two uh, uh, regions now, one inside this volume and the other outside this volume, but within the surface S. What we are going to do is to minimize this volume here as much as possible, and then uh, uh, or minimize the contributions from this surface S and get a more or less accurate results. Now we have two surfaces, surface S, both capital letters, and S prime, and the contributions at this point P can be regarded as contributions from S plus the contributions from S prime. And that's why the Green's theorem has now, as on the left hand side, it has two integrals, one on the surface S and one on the surface S prime, and if you do that, okay, you take the second surface to the right hand side. This is around S and this is around S prime, and the integrand remains the same on both sides, and therefore okay, this S here, remember, it's not the surface, it's the distance from this, and therefore you can represent both distance from P to the surface S prime and S with the same variable S. You take the differentiation. Okay, remember we are taking the differentiation with respect to n according to this equation, but that, as we said, this is del n e to the power I k s over s, or that is dou by dou s of e to the power I k s by s along the normal, or that means this is cos the angle between n, unit vector n, and the vector s, if you like to say that. But these are this n is along the normal and s is going to be along the normal, and therefore this is going to be 0, and therefore cos 0 is 1, and that's why you just take the differentiation with respect to s, because n uh, uh, for this surface S, which is a spherical surface, n is pointing outwards because pointing into the volume. That's what was the definition of n was. And then this radius is along that normal, and therefore uh, they are all equal. Otherwise, you should have had a n s cos of that somewhere here, but this that is 1 in our case. Now you take okay, you rearrange the terms, u times e to the case by s times this, and here we have e to the case by s here it says, and on the surface, because the radius of this sphere we have taken as epsilon, now on the surface, that's what we are interested in terms of the solid angle, you get e to the power I k epsilon by epsilon I k epsilon times the area element in terms of solid angle on this surface is, as you know, it is okay. What is solid angle? Omega is uh, um, area divided by r square, and therefore area ds is r square, okay, d omega, and that's what you have written here, epsilon square d omega. And now let apply the limit. We want to make this sphere as small as possible. We want to take epsilon going to 0, which means what is the value of epsilon? Here on the first term we will have an epsilon, because this epsilon 0 square times this epsilon will give you an epsilon remaining on the numerator, and if that epsilon goes to 0, this term will go to 0. But here the second term u e to the power I k epsilon, and the second term is minus 1 by epsilon square times epsilon square from here, that will be again independent of epsilon, that remains. And here again we have an epsilon on the numerator, and therefore when you apply the limit as epsilon tends to 0, the terms on the RHS other than the second term vanishes. What is second term? The second term will be therefore omega u e to the power I, okay, here you have a minus, and minus minus plus, e to the power I k epsilon d omega, and also this epsilon goes to 0, and therefore this disappears, that's equal to 1, and therefore the value when epsilon tends to 0 means u becomes the value at the point up, the value of the at the point p, and therefore this will be up times integral d omega, or that is, if you integrate over the 4 pi radians, that becomes 4 pi up, and that's what we get here. Okay, here this goes to 1 as epsilon tends to 0, and therefore this is what you will get. Now we can rewrite the equation on the RHS of the main equation. You have this, and therefore the field distribution at the point P as a function will be 1 by 4 pi times, okay, this integral here, where u is our scalar wave function, and this is known as Kirchoff's integral theorem. Now to sum up, Kirchoff's integral theorem relates the value of any scalar wave function at any point P inside an arbitrary closed surface to the value of the function at the surface. Okay. This is relating the value function at the surface. Okay, and one could apply Kirchoff's integral theorem to diffraction, and in that case u becomes the optical disturbance. Okay, that is what we call it, optical disturbance. That's because we cannot call it an electric field vector because it's a scalar. It's a scalar quantity, and we can call it an optical. If it's a spherical wave, you can take this expression here, e to the power IKS by s, and if it's a planar wave function, you can take e to the power IKS, and similarly like that. And it's a scalar approximation, as I said, because the vector is treatment is more rigorous, and also something that is very long derivation. However, u square will, you can represent the irradiance or the intensity which we are interested in, or which we experience with your eye, or which you experience with your measuring instrument or a camera, whatever you use. U square is regarded, in this case of scalar wave function, U square is regarded as the irradiance or intensity of the wave. Hope you have had some brief explanation of Kirchoff integral theorem, and with that we stop for with that topic. Thank you.